Everybody still hear me okay?
Yeah, you're all good.
Okay. All right.
Mm-hmm.
Let's see. So in terms of bonding theory, the thing we'll mostly talk about during the semester is hybridization theory, talking about these atomic orbitals coming together as wave functions. I just want to introduce to bonding ideas briefly, although we won't really need it until next semester in 202 for those who take it, is this idea of molecular bonding theory. Now, very similar to hybridization, for every atomic orbital that's involved in the bonding, we can describe a new molecular orbital. We normally see this when we have delocalized electron systems. Delocalized because the electrons are not localized between two atoms, they're delocalized over some extended structure. And most of the time, this happens when we have atomic orbitals on more than two atoms connected to each other in a line. Classic example of this is something like benzene, where we have a carbon ring of 6 atoms. Let's see if I can try and improvise this. Be kind to my drawings, I'm just using my cursor. So 6 carbons in a ring, and this is the ugly part. All of these carbons are, whoops, let me undo that. All of these carbons are sp2 hybridized, which means they have an atomic orbital above and below the plane, which I'll draw very badly here. Now I'm drawing them a little bit on the small side just to give a bit of clarity. But for every carbon, it's got a neighbor on two sides and atomic orbitals on two sides to that original orbital it's touching and overlapping with. So even though we try and sometimes draw these Lewis structures with double bonds for something like benzene, they're not localized between the two atoms, they're delocalized around that entire circuit of atomic orbitals which are linked up. And so it's sometimes better to think about these chemical bonds through what we call molecular bonding theory. The number of atomic orbitals describes the number of molecular orbitals, and we see them stack up from low to high energy. And we're talking about these orbitals coming together increasingly destructively as we move to higher and higher energy levels. So for example, something like hydrogen, using two orbitals, we get two molecular orbitals, one of which is lower in energy than the original atomic orbitals, and one of which is higher in energy than the original molecular orbitals. That second molecular orbital is higher in energy because the electrons are occupying space outside of that plane between the two nuclei. And it creates what we call a nodal plane. This is what makes this second orbital higher in energy, because we're getting protons being repelled by protons in the other nucleus. There's no blanket of electrons between the two nuclei. So the two orbitals coming together to produce a molecular orbital constructively and lower in energy, that's what we call a bonding molecular orbital. And the two orbitals coming in together out of phase destructively to produce this high energy molecular orbital. This is what we sometimes refer to as an anti-bonding molecular orbital. The most complicated case that we'll look at eventually next semester is with carbon in a benzene ring. We've got 6 carbons, 6 atomic orbitals, and so we'll produce 6 molecular orbitals, 3 of which will be bonding because they're lower in energy than the original atomic orbitals, and 3 of which will be antibonding because they are higher in energy than the original atomic orbitals. Okay, and that's as much really I want to talk about molecular orbital theory in this semester. All we really need for this semester is hybrid theory, and it's even simpler than it was in 151 and 152 because we're only talking about sp3, sp2, and sp hybrid theory. sp3 when it's all single bonds around the carbon, sp2 when there's a double bond, so normally alkenes, and then sp when it's a triple bond in the molecule, so normally alkynes, or maybe a carbon atom with 2 separate double bonds. Excuse me, I think that's my son trying to just play games with me through the door. All right. So when we're drawing pictures of molecules, you'd often in 151 and 152 draw Lewis structures, which we've just quickly touched on today. One of the things that we sometimes see when drawing these structural formulas is that chemists get lazy and they don't add the lone pairs in. We see a good example here with methanol. This is how ethanol, 2 carbons in the main chain, of course. This is how you might see ethanol being portrayed, but it is a little bit lazy in its portrayal because the oxygen here has not been shown with an octet. We're only seeing its chemical bonds, and we've left out its lone pairs of electrons. It's something quite commonly done because it's very common to see oxygen with 2 bonds and 2 lone pairs. So if we're being really picky, we should really draw the ethanol like this, with those 2 lone pairs added in. Unfortunately, this kind of laziness is often seen when drawing organic molecules in textbooks. So just watch out for it, be aware of it. The halogens, of course, they have 1 chemical bond normally. How do we know this? Because they're the last but 1 element in each row. And as we said, the combining power is how many additional boxes we have to count to reach the end of the row. So an element like fluorine normally is chemically bonded to just 1 other element. So I'll draw a bond in here to some atom, which means to make up its octet, it normally has 6 electrons drawn as lone pairs, 3 lone pairs. That's a proper depiction of a halogen. But do be aware that your textbooks will quite often just draw fluorine like that, just as they'll draw oxygen with just 2 chemical bonds. You have to assume that the lone pairs are there. Likewise, another common shortcut you'll see is for nitrogen. Nitrogen needs 3 more boxes to reach the end of its row in the periodic table. So we normally expect 3 chemical bonds, but again, that doesn't make for an octet. So even if the structure is drawn like this, the implication is that there's a lone pair on the nitrogen making up its octet. If that lone pair wasn't there, not only would the nitrogen not have a completed shell, it would have a formal charge. formal charge can be calculated by taking the periodic table position of the element and subtracting from that the number of electrons which belong to the element in the Lewis structure. So of course in the periodic table, nitrogen is the fifth element in that period. We see 1, 2, 3 chemical bonds here, each bond being a pair of electrons, and one of those electrons each time belongs to the nitrogen. It shared electrons to make covalent bonds. So that would only suggest that it controls 3 of the 6 electrons around it, which would give it a +2 charge, formally. But there's nothing written in the top right-hand corner. So that's telling us that the lone pair is there. Even if you don't show the lone pairs around an atom, you could not neglect to show that there was a formal charge. So if there's nothing written, you can assume it can be electrically neutral, which means that there must be a lone pair on the nitrogen. Likewise, if there's no suggested electrical charge on an oxygen, it's implying that there are 2 lone pairs of electrons around the oxygen. So with the 1, 2, 3 electrons and the lone pair which belong to it, 5 minus 5, 0 charge on the nitrogen atom. Again, that should be something that Mr. Mackenzie would have gone over as part of 151 and 152. Chemists get lazy when it comes to their organic molecules, and so watch out for lone pairs which are implied but have not been drawn in the structure. Remember your combining power. Hydrogen is the first element in the first row, so we expect 1 bond. Carbon is the 4th element, so we expect 4 chemical bonds. Nitrogen is the 5th element in the row. It needs 1, 2, 3 more electrons, so we expect 3 chemical bonds. Oxygen is the 6th element in the row. It needs just 2 more boxes to reach the end of the row, so we expect normally 2 chemical bonds. Any questions about that? Still doing okay? Again, it should be pretty much just straightforward revision, to be fair. Now, something that might be new is the idea of drawing line angle formulas for organic molecules. So many organic molecules that we have to work with could have maybe 30 or 40 carbons in a main chain, sometimes even hundreds of atoms connected together through a carbon backbone. And so chemists again get lazy and we start to omit some of the detail, assuming that people understand what these emissions are, just like emitting lone pairs of electrons from the Lewis structure. So what chemists said was that because the molecule is made up of a carbon backbone, we don't really need to draw in the carbon atoms. We won't bother with a chemical symbol for carbon. Likewise, the majority of the remainder of the molecule is just hydrogen, so we won't bother writing in the hydrogen symbol either. In fact, we only normally write in a chemical symbol for an atom in 2 ways. One, if it's a non-carbon or non-hydrogen atom, and also we occasionally do put in the hydrogen if it's part of some kind of functional group, like an alcohol group, which is OH. Then we'll add the hydrogen back in to clarify the functionality. So if we're not writing in the carbon symbols and not writing in the hydrogen symbols, how do we recognize the structure of the molecule? Well, I'm glad you asked. So what we do is highlight the chemical bonds themselves between the carbons and hydrogens. Or the carbons themselves, I should say, rather. Excuse me. So I can move this up a little bit. So you can still see the structural formulas. And then we've got these line angle formulas at the bottom. The lines you're seeing are emphasizing and showing the carbon-to-carbon bonds. So every time the line reaches a point, or every time the line changes direction, it's the implied position of a carbon atom. So for our first one here with ethane, we're saying that there's a carbon atom at that end, there's a carbon atom at that end, and this line is representing the bond between the carbons. Then with hexane, when we've got a line of carbons strung together, we can highlight where each carbon is in the molecule by getting the line to change direction, or zigzag, which is exactly how the molecule appears in real life because of repulsion forces between bonding pairs. So each point is the implied position of a carbon atom. Likewise with a cyclohexane ring, each time the bond changes direction, is the implied position of a carbon atom. Now, of course, the carbons are bonded to each other and also bonded to hydrogens to make up the molecule. But we don't even show the carbon to hydrogen bonds as lines normally. So at this point, when we look at a carbon in the line angle formula, of course, a carbon needs an octet, which means it needs 4 bonds. So we subtract the number of bonds which are shown in the structure and realize that the final answer has to be 0. So if we're only seeing one line coming from the carbon, the implication is that there are free hydrogens attached. And we could draw those free hydrogens back in. Very poorly, because I'm trying to use my cursor as a pen. Like that. And the same, of course, on the other side. If the carbon has 2 lines coming from it, that implies 2 carbon-to-carbon bonds, and therefore our little piece of math here, 4 minus something to be 0, 2 bonds being shown. So there's 2 bonds which are emitted, 2 carbon-to-hydrogen bonds. So from here we can draw 2 bonds to hydrogens. Here we can show 2 bonds to hydrogens. The same on the next one and the previous one. And then right at the end, there's only 1 bond coming from the carbon. So to complete its octet, the implication is 3 carbon to hydrogen bonds. Likewise with our cyclohexane, from each point there's 2 bonds, 2 lines coming away from that point. So to make up our octet, the implication is that there are 2 carbon to hydrogen bonds emitted. Any questions about those ones? We can do some more practice tomorrow, but for most of the semester, we should be drawing our hydrocarbons and structures using line angle formulas. You only emphasize the chemical bonds between one carbon and its neighboring carbons. And we can imply how many hydrogens are attached as we try and make up that octet with 8 electrons around each carbon position. Okay, let's see what I've got left. Just a bit of a summary. Remember, we normally expect to see 4 carbon bonds around any one carbon. It's very unusual to see lone pairs on a carbon. It does occasionally happen, but it's not normal. It's normally 4 chemical bonds. Normally nitrogen has 3 bonds and a lone pair. That could be 3 separate bonds, 3 sigma bonds, or 2 sigma bonds and a pi bond with a lone pair, or maybe 1 sigma bond with 2 pi bonds and that lone pair. It needs to make up its octet normally. If you see a nitrogen with a positive charge, it's because the nitrogen, instead of a lone pair, has a 4th chemical bond. It only controls 1, 2, 3, 4 of the 8 electrons around it. So a positive charge on a nitrogen tells you it only has 4 chemical bonds, and there isn't a lone pair that's being omitted. Similarly with oxygen, the natural arrangement environment for an oxygen is 2 bonds and 2 lone pairs. Again, that's from our combining power ideas of the periodic table. From oxygen's position, we need to count 2 more boxes to reach the noble gas at the end of that row, neon. And so we expect 2 chemical bonds, and so its octet is made up by 2 lone pairs. It could be 2 single bonds and 2 lone pairs, or it could be a sigma bond and a pi bond with the 2 lone pairs. If the oxygen has a positive formal charge, that means one of the lone pairs has turned into a bonding pair. Think of something like a oxonium ion and hydronium ions for acidity. Or we could have an anion on the oxygen as an oxide. That's when it has 1 sigma bond and 1, 2, 3 lone pairs. It's controlling more electrons than it normally should. Instead of controlling 6 of the 8 electrons around it, it controls 1, 2, 3, 4, 5, 6, and 1 from the bond, 7. Standard environments for a phosphorus atom. Remember, it's the 5th element in the 3rd row of the table, and it needs 3 more boxes, 3 more electrons to complete its shell. And so normally for phosphorus, we would see phosphorus with 1, 2, 3 bonds. And so even if the electron pair isn't drawn, the implication is, to make its octet, it also has a lone pair, just like nitrogen directly above it in the table. Elements of the same group, so similar chemical properties. Silicon, directly below carbon and chemically similar to carbon, is the 4th element in the 3rd row. We have to count another 4 boxes to reach the end of the row, so we normally expect 4 chemical bonds, just like carbon. And then sulfur, below oxygen in the periodic table, acts normally like oxygen. It has 6 electrons. It needs another 2 boxes to reach the end of the row, so we expect 2 chemical bonds normally, and making up its octet, normally 2 lone pairs, just like an oxygen. Just keep in mind that sulfur is one of our elements which is hypervalent. It can break the octet rule because it can have 8, 10 or even 12 electrons around it in its shell because it can sneak electron pairs into its d subshell. All right, I can't really much more left. So just some practice examples for line angle formulas. Let's try these before we finish off, but I'll give you a couple of minutes first because I'm going to grab a quick drink. So there's the line angle formulas. Write out the structural formulas that you're probably used to, showing the carbons and hydrogens. And after that, take these structural formulas and turn them back into a line angle formula, emphasizing just the carbon to carbon bonds. So take a piece of paper and try those for the next 5 minutes. We'll come back and check our answers, and I think we're done for today. We'll come back tomorrow at 2 and do this more of the same, well, similar stuff, but on chapter 2, and fingers crossed, I'll have a negative test that I can celebrate tomorrow. Any questions before we take another 5-minute break? Doing okay? So this should hopefully be just dusting off some cobwebs and remembering some things that you might have forgotten over the summer. Okay, back in. Oh, yes.
Yeah, I think some of this is coming back to me now.
We can certainly do some more practice tomorrow as well. Now remember, our first big test is going to be on chapter 1 and chapter 2 together. And as you look on Desire to Learn, as I think we talked about yesterday, as I talked about in the video in the news feed, there are practice exams on Desire to Learn for chapters 1 and 2. If you take a look at a couple of them, you'll see a very kind of regular pattern to the kind of questions I'm asking. If you try those practice exams, fill them in and hand them to me in class, I'll grade them within 24 hours and give them back to you as some feedback. Okay? So there's always plenty of opportunity for feedback. I'm nice. My mum says I'm nice, so it must be true. Right, back in 5. And Skylar too, yeah. Oh boy. So I've just been cleaning makeup off my cat because my 5-year-old daughter thought it would be a good idea to put eyeshadow and blush on a cat. Anyway, that wasn't what I thought my day had in store for me. She often actually, my daughter, she likes to, she's so keen on makeup, she'll often paint my fingernails and toenails as well. So if I come in with gloriously painted fingernails, then you know it's my daughter. We were on a boat trip earlier this summer when things seemed safe enough for that. And just t-shirt and shorts on this boat trip in St. Louis. And I'd just taken my sandals off. And I'd forgotten that my daughter had painted my toenails that morning before we went out. And so we're in this kind of leisure boat out in the river. And I could see the couple across from us. And there's this lady looking about, and she kind of looks at my toes and sees that I've got painted toenails, and she gives her husband a dig and to look at my toenails. And they're beautiful pink. Right, let's get this finished off and let people go for the day. So turning this line angle formula back into a normal structural formula, remember every point is the position of a carbon. So let's use black this time. Black is the new black. So if I start from this apex point here, there's a carbon in that position, and there's a bond straight down to another carbon. Let me start with the skeleton, and then down to the left is another carbon, down to the right, another carbon, and then we go up to a carbon here. Of course, badly drawn because we're using a cursor. And then another carbon down there. And then we look for octets. This carbon can only see 2 electrons, so there's 1, 2, 3 bonds, 2 hydrogens implied to make up that octet. Next door, there's 1, 2, 3 bonds, so there's an implied 4th bond to a hydrogen atom. Down at the left corner again, 3 bonds for 3 hydrogens to make up the octet of the carbon. And then on the other side, 3 hydrogens down here, which I'll try and squeeze in badly. Carbon above, 1, 2, 3 bonds. So there's 1 remaining bond to a hydrogen to make up the octet. And then another 3 on our final carbon there. Next one, again, starting from this end of the carbon chain, carbon there, and down to the next carbon. Not easy using a mouse pad. Trying to do this, and then one last carbon there. I'm going to be lazy this time. I'm just going to draw in the hydrogens in a condensed formula. So CH3 making up the octet, and 1 hydrogen there. CH3, a terminal methyl group again. CH2 there. And CH3 at the end. Final one, if I take this top corner here, so carbon up there, down to this carbon at the center of the X, carbon here, carbon here, oh dear. Sounds like my daughter is asking Mummy if she can have a baby sister again. Well, I don't think so. So there's our carbon skeleton, again adding the hydrogens to make up. CH3, 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 4 4 bonds to this carbon, so no hydrogens attached. CH2 with 2 bonds. And a terminal carbon again, so CH3. I can't do anything about that blush just now. Okay, ready for the last 3, doing the line angle formulas. Move the table down. Okay. So now this time we have the structural formula. We're going to turn it into a line angle formula. So we'll start with this carbon here. Go straight down to the next carbon. And then we go left and right, sloping down either side. Whoop. Oh, that's terrible. That's not much better, but... And then from there we go up again. Then from there we go to this carbon to nitrogen bond. So a bond up, but that is a triple bond. So again, if the line changes direction or changes thickness, it's the implied position of a carbon. And on the far side, it's a nitrogen, non-carbon, non-hydrogen. So we do put the chemical symbol in. Cat. Second one, we've got a ring of carbons. Oh, actually, I can do this a bit better because I can invoke some lines. So if I go like this, there we go. That looks sexier. Much better. And then there's 2 carbon to carbon double bonds down each side. And then carbon to oxygen double bonds at the top and the bottom. Should have left myself more room, but never mind. Put those oxygens in, squeeze them in. Anything else there? That's it. And the last one, I'm going to start with the 5-membered carbon ring. There's a double bond there. Methyl group CH3 there. One there. And a acetylene link down there. I haven't left myself enough room again. I'm going to draw this at a slightly weird angle. And just extend that a little bit further. So it looks about the same length as the other ones. So carbon, triple bond carbon, carbon, triple bond carbon. That should be it. So this is how we'll mostly represent organic molecules over the course of the semester. These line angle formulas which emphasize the carbon backbone and the carbon to carbon bonds and we can fill up the octet of each carbon normally by just imagining in the appropriate amount of hydrogen. Anything else like sulfur, oxygen, nitrogen, etc., we'll just draw those symbols in. Any questions before we finish up? I imagine we'll get on to resonance tomorrow. So I think there is a folder for what I call organic chem talk videos. I do have some there. I might have to update it, but I think I do have something on line angle formulas and resonance. If you get the chance, try and take a look at those in the next couple of days. That will help. But the resonance is probably the big thing that we'll be looking at tomorrow and for chapter 2. And it tends to be probably the stickiest bit of chapter 2. Okay, I think that gets us really through chapter 1 material. I'll put this video up on Desire to Learn if people want to view it later. And just let me know if there's any questions. People can text me as well as using email. Texting tends to be faster because, of course, like most people, I'm a slave to my phone. And so I'm never very far away from it. So number for texting, let's see, is 618 364 5546. It could be something as simple as, here's a problem in the McMurray textbook that I don't understand. Click, take a picture. I can write out an answer if it's necessary. Take a picture and send it back. Boom! Excellent communication. Tell me about your troubles. Please don't suffer in silence. You're not alone. I'm here to help. Okay, guys. I'll see everybody back here tomorrow. Same Zoom time, same Zoom channel. And I'll bid everybody a good day. Bye. Just like that, Dr. Elliot was all alone.
Well, I'll be seeing you then. Goodbye.
Super duper. Bye. Oh, glasses.